Thank you for teaching me how to skate, Mr. Lee.
You're welcome, Logan.
Watch out, Mr. Lee, I'm out of control!
The system is a student, therefore the events revolve around the student that is in control. His mass is 7 kg. The starting velocity is 1 meter per second, and it is a negative because he is traveling in the negative direction. His ending velocity is 0 meter per second as he collides with people at number 2. The displacement is 0.5 meters, and we can tell that there's an acceleration because there's a difference between the starting velocity and the ending velocity. And we can tell that there is a balance and a new force from having acceleration. The only force that is acting on the system is the applied force, therefore F net equals applied force, but the applied force is null.
So, for the motion dot theorem of the scalar control, it starts at event 1 and moves in a negative direction to event 2. But we know that it's slowing down, which is represented by the closing of the gaps between the dots. For the position time graph of the scalar control, it starts at event 1 and moves in a negative direction to event 2. But notice how he never reaches the x-axis because he never reaches the origin. For the velocity time graph, he starts at high velocity at event 1 and moves it slows down until event 2, where he comes to a complete stop. Likewise, for the velocity vectors at event 1, his velocity is quite high, at event 2, he is at a rest, and so it is just a dot. Since we know he is moving in a negative direction, and he is slowing down, that must mean that acceleration is positive, which is represented by the acceleration time graph. For the interaction diagram, we have the normal force from the ice pushing him upwards, the gravitational force from the earth pushing him downwards, and the applied force from the skater pushing him in the opposite direction. We are also assuming that there is no friction because he is on ice. For the force diagram of the scalar control, the normal force is pushing him upwards, the gravitational force is pushing him downwards, but they're balanced, so he's not moving on the y-axis. Since the only force on the x-axis is the applied force, F net x equals Fa. But Fa is pushing him in the positive direction, and therefore, the acceleration is also positive.
With the given mass, the initial and final velocity, and the displacement, we can use one of the big five equations to find the acceleration. The equation we decided to use was the final velocity squared equals the initial velocity squared plus 2 multiplied by the acceleration and the displacement. So after rearranging the equation, we get the acceleration equals the final velocity squared subtracted by the initial velocity squared divided by 2 multiplied by the displacement. So after plugging in the numbers, we find that the acceleration is 1 meters per second squared in a positive direction. To find the net force, we use the equation F net equals mass times acceleration. So after plugging in our mass and the acceleration we find that the net force is 70 newtons in a positive direction. And since the net force is equal to the force applied, we can conclude that the applied force is equal to 70 newtons in a positive direction.
I guess you didn't apply enough force.